Okay, good morning. I'm going to go through quickly here the problems from ICP 6, the in-class problem set 6. Let's go to number 1, the integral. It's an indefinite integral. There's no a and there's no b. Therefore, the answer is going to be another formula, and it needs to have a plus c at the end of it. We'll talk about that another time. But right now, what we've got is we've got to take the antiderivative of each term. Can it be simplified at all? No. It's a regular polynomial. Notice the terms are there, just x squared and x. Therefore, it is just going to be a straightforward, use the basic rules. Okay, so the first one is raise the power by 1 and divide by that new power. Second term, raise the power by 1, divide by that new power, add c, and then simplify. So we end up with x to the third, the 3's cancel, and the 2 goes into the 4, and that gives me negative 2x squared plus c. Answer. Number 2, integral of pi plus 3 over x to the 4th. Okay, notice difference this time. It's again indefinite integral, so I'm going to need a plus c. But this time I've got a constant only, and it's a pi, so it's not like just a number. But we've got a pi there. That is a constant. What do you do if it's just a 2? It's just like a 2 or a 5. Okay? And then the second term has got an x to the 4th in the denominator. That's going to be a negative. We're going to bring that up. So this one has something we want to modify before we start the antidifferentiation. So I still maintain the integral symbol, and nothing changed about the pi. I'm going to leave it there. And now I'm going to bring up the x to the 4th, and that's going to make it x to the negative 4 on top. Okay, and now I'm ready to take the antiderivative. So I need to hit each term. The antiderivative of a constant. Attach an x to the first power. And then the next term, I'm going to write this one out a little bit more with the rules. The idea that you have a negative value, x to the negative 4, add 1, and divide by that new power. Raise the power by 1. That makes it a negative 3, and I'm going to divide by that new power. That's a habit I got into of just writing it out up on top and then doing the work on the bottom. It saves a step in the process. And then I've got to remember that this is where, if I was doing it officially, I would add a plus c. And if you do that at the end of the problem, that's totally fine. But remember that you do need a plus c if it's an indefinite integral. There's no a and there's no b. There's no a, there's no b. And that's an indefinite integral. Okay, now we need to simplify. So now we've got the pi x doesn't change. Now that negative 3 in the denominator is a multiplicative factor, dividing by negative. That negative sign is going to need to come upstairs, and the 3's cancel, so I actually end up with a subtraction minus x to the negative 3 plus c, and then I'll ask you to get rid of negative exponents for final answers, and that ends up being pi x minus 1 over x to the 3rd plus c. Done. Notice that the power in the denominator went down by 1, and the plus became a negative as a result of that exponent in the denominator coming up and becoming negative. Okay? Change of sign, and the exponent decreased by 1. Number 3, the integral of 8 over square root of x. dx is a very critical part of the problem. All right, now we've got a fractional exponent, that square root, and it's in the denominator, so it's a negative fraction. So let's reconvert it. The integral stays. We don't start integrating until we're ready for it, okay? Till everything's been converted and it's ready. So then we've got 8. That square root down at the bottom is x to the 1/2. Bring it upstairs, it's negative 1/2. So we've got x to the negative 1/2 dx. Now it's ready to go. The integral sign is still there, the integral bar is still there, and the dx is still there. So now it's ready for integration. So what do I do? Now the integration bar and the dx both go away. Raise the power by 1. I'm going to write it out. Raise the power by 1. I'll give it a common denominator. And now I divide by the new power. That's going to be negative 1/2 plus 2/2 is positive 1/2. Divide by that new power. All right. And then as a result, let's go one more line over here. That gives us, we're dividing by a fraction, dividing by 1/2. That means you flip and multiply. That becomes 2/1 times 8. And we've got x to the positive 1/2. And like I have said, and one thing I left off here, the integral bar and the dx went away. I didn't add a plus c. That's where it would come in. All right. And then we've got a plus c there. So the final answer is going to be, we've got the 16, and the x to the 1/2 is up top now. So that is just going to be the square root of x plus c. Notice the square root started in the problem in the denominator, and we ended up with it in the numerator. Interesting. And the idea of having to multiply that 8 by 2. So the final answer is 16 squared of x plus c. Number 4. This time we've got a definite integral. When it's a definite integral, the answer should be a number. It should be an actual value is the final result. As long as the definite integral has numeric a and numeric b, then the answer should be a number. So we end up with here, there's nothing to simplify. Raise the power by 1 and divide by that new power. And the simplification of the bar afterwards to remind us of a to b is the traditional way I've seen it written most of the time. The book does something a little different. They do brackets around the fraction. I'll show that in a second. But right now, the fundamental theorem of calculus says that the integral of f of x dx equals cap f of b minus cap f of a. All right. So now we need to get the integral. The cap f is this x cubed over 3. That's cap f. Here's little f, the lowercase. Cap f is x cubed over 3. We've got it. Plug in the b, which is 2, and plug in the a, subtraction sign. You plug in the a, which is -1, and keep track of that minus sign. You're subtracting, and you've got a minus sign. So you've got to keep track of your signs. This is where a lot of mistakes happen at first, when first learning it. All right, this turns out to be 2 cubed, 8 over 3. We've got -1 to the third. That is -1, and -1 and -1 makes a plus 1/3. That turns out to be 9/3, and that is equal to 3. Notice there's no plus c. The final answer is 3, a number. You've got a definite integral. The answer should be a number, and it is 3. Also, all 3 of the first problems, you've got the indefinite integral. You take the derivative of your answer, and you should get what you started with. The derivative of the constant is 0, and the derivative of each term should give you the numbers that you started with. And if it's not the same that you started with, something's wrong, okay? You did something wrong. Make sure you check that. This one, the definite integral, you can plug into your calculator and check it out. You do this in Math 9. Math 9, infinite, the function integration, the FNINT. Use that and verify that your answer is 3. Number 5, another definite integral. We got 0 to 1. This is 2e to the x. This one's, I'll use the word entertaining a little bit, because watch what happens here. What's the derivative of 2e to the x? 2e to the x. What's the antiderivative of 2e to the x? It's 2e to the x. So the idea here is the cap f, this is little f, cap f in this situation, let's go back to the fundamental theorem. This is a little f here, lowercase, those are caps. Okay, so we get 2e to the x, there's our cap f, and that's going from 0 to 1. And typically I will ask of you on an assessment of some kind, either to give the exact answer or round it to 4 decimal places, let's say, a certain number of decimal places. Let's say 4 decimal places in this problem, okay? Let's do it both ways. So we end up with, I want the exact answer and I want the answer rounded to 4 decimal places. So I've got cap f now, I need to plug in b and a. So now I've got 2e to the 1 minus 2e to the 0, which is, and be careful with that e to the 0, a lot of people that have that become a 0 for them, e to the 0 is equal to 1. So you've got 2e to the 1, which is 2e minus 2. And the end result is, that is a simplification. Now, typically, when we've got an x in there, a variable of some time, we have a tendency, and I've encouraged you to factor out the 2, you know, because we're trying to figure out what the zeros are. Well, this e is not an x. So factoring out the 2 isn't really helpful. It does factor, but this is the good exact answer for that problem. Now let's check out the result of plugging it into our calculator and seeing what 2e minus 2 is to 4 decimal places. So I've got 2e, and I get 5.43, yada, yada, yada. Subtract 2 from that, and I've got 3. I'm going to write out 5 decimal places just for the sake of rounding, because to determine what we're going to do, 4, 3, 6, 5, 6, and the rest of the numbers there. Okay, so I want 4 decimal places. Look to the next number. Is it 5 or above? Yes, it is, so I round up. So the final answer to 4 decimal places, the approximation, is 3.4366. All right, I'm going to go to a new sheet here and do number 6. Questions on that, you know, keep track of stuff. If you got questions that develop from this, make sure you get in touch with me and let me know. All right, so now let's go on to number 7. No, this is number 6, number 6. Okay, we've got another definite integral. So the answer should be a number. All right, notice that. And we've got another situation here to contend with. We got a rational fraction, you know, we got a rational function here. We've got a numerator and a denominator in this case. And that can be confusing because sometimes if you're taking a derivative, you got to use the quotient rule, so to speak. But in this situation right now, you can simplify this a little bit by, we've got a single term in the denominator. Notice that. If you've got a single term in the denominator, that can become 2 fractions added together. That can be a simpler problem, and it really is in this case. So take a look at this. So if I rewrite this, I haven't started taking the antiderivative yet, but I'm going to break this into, I'm going to move the x under the 1, make it 1 over x, plus x squared over x, which we can simplify. I'll do that in the next step. That's another way to write that fraction, the rational function. And again, we haven't started integrating yet. So the integral bar and the dx are still there. Let's do one more step to clean it up. That's 1 to 2 of 1 over x plus that x squared over x simplifies to x dx. Okay, now we're going to start integrating. And I want to point out to you on other problems we've done before where there's an x in the denominator, that means we bring it up and make it a negative exponent. Look what happens if we do that this time. We've got x to the 1 in the denominator. You bring that upstairs, that's x to the negative 1. You integrate, add 1, and divide by the new exponent. Negative 1 plus 1 is 0. And then you divide by 0, which is a flag goes off. Okay, let that be a flag. This is a special case, the 1 over x. That's that. If you remember what the derivative of natural log is, derivative of natural log is 1 over x. So the antiderivative of 1 over x is natural log. So in this case, we're going to start the antiderivative now. And we've got the natural log of absolute value of x is a good thing to recognize. Notice both of the numbers a and b are both positive, so that absolute value sign can fade away in just a second. But it's important to remember that that absolute value sign is critical in problems where you've got negative values. It makes a difference in the answer significantly. Okay, And now we take the integral of the antiderivative of x, that's x to the 1, so we add 1 to the exponent and divide by that new exponent. There is our cap f, and it's going from 1 to 2. So now it's a matter of plugging in that this is cap f, so now we need plug in b and plug in a and do a subtraction. So we end up with the natural log of 2, again, absolute value I'm going to take off and not a critical. Plug in b to both values, to both terms of this function of cap f, okay? I don't need the parentheses because they're both positive, but it's a reminder, this is f of b. Now I'm going to subtract f of a. Parentheses are crucial on f of a. Because of the fact you're subtracting and there's two terms there, you got to hit the negative sign on both of them. So we get the natural log of now we're plugging in a. So plug in 1, natural log of 1. I guess that I'll just put a 1 there. And you'll get the habit after a while of beginning to recognize right away natural log of 1, e to what power equals 1? That is equal to 0. So that's going to be 0 in just a second. And then we plug in 1 into the second term. All right, and that gives us then, we've got natural log of 2 plus 4 over 2, which is 2. I'm going to distribute the minus sign, and we've got a minus natural log of 1. Check it on your calculator at first if you need to, but that's 0. And distribute the minus sign, I got a minus 1/2. So I end up with the natural log of 2 plus 4/2. I'm going to get a common denominator there, so I can just get that picture going. And the answer turns out to be the natural log of 2 plus 3/2. Exact answer, that's a good one. You could write that as 1.5 if you wanted to, but that is an exact answer. If you plug in natural log, you get a never-ending decimal type thing. All right? And then let's figure out what the other value is. And you might want to go through the process of actually plugging that original function into your calculator, but right now I'm just going to do natural log of 2 and add to that 1.5. The answer we had, convert this to 4 decimal places, and that equals 2.19314, yada yada. Tell you what, let me talk about this one just a second. Several people made a mistake on the last assessment in that we got 4 places. That's the 1 here. The next number is a 4, so that is less than 5. But a few of you saw that 7 and thought, okay, 4, 7, therefore it's going to round up to 5. Therefore, you rounded up the 1 to a 2, and that is incorrect, okay? The idea is you look at that 4th decimal place, look at the next number right now, before it's been rounded at all. Is it 5 or above? No. That means you round down. So the final answer is 2.1931, rounded to 4 places. So that's an approximate answer, okay? Then we look at number 7. And number 7 is a nice little, I don't need much space on this one because it's a straightforward problem. It is and there's a 1 there. And what's the rational function that's coming here is an interesting one because of the fact that if you look on that formula sheet that I gave you along with this quiz, take a second and look at it. Look at the bottom right formula on the integral listing, okay? Remember, we went through this earlier on and we didn't dwell on it really a long period of time. But if you notice that the integral of 1 over 1 plus x squared is a specific value. This is one that you need to be able to recognize. And especially if you're going on to Calc 2, you're going to need to be able to recognize this type of material in solving problems, okay? This specific example. Notice that the derivative of the inverse tangent function is 1 over 1 plus x squared. So that means the antiderivative of 1 over 1 plus x squared is the inverse tangent function. So the answer to this problem is going to be the integral of 1 over 1 plus x squared is inverse tan of x. And we're going from 0 to 1. And this is the one I want to talk about just a little bit. So we plug in that b, and we get the inverse tan of 1 minus the inverse tan of 0. All right, and remember what those things are. The angle whose tangent is 1. Where does it happen that the tangent is equal to 1? Tangent is sine over cosine. Tangent equals 1 means sine is the same value as cosine. Where does that happen on the unit circle? The only place sine and cosine are the same is here at 45 degrees, pi over 4, and down here at 180 and 45, 225 degrees, which is 5 pi over 4. So the answer to this situation that is given in the initial interval here, we get pi over 4. You plug this into your calculator, and you'll see you'll get a decimal that isn't really recognizable as an obvious. That's pi over 4. So, but we end up with, this situation is pi over 4, the angle is pi over 4, and the angle whose tangent is 0, sine over cosine is 0 means sine is 0. Where is sine of 0 equal to 0? That's equal at 0 degrees. So we're at 0, all right? And that therefore equals pi over 4. So the exact answer is pi over 4. Now plug pi over 4 into your calculator. Second up divided by 4 equals 0.78539, yada, yada. And that turns out to be 0.7854. So the approximated answer to 4 decimal places, 0.7854. And then if you go in and do inverse tan, second tan on your calculator, and put in 1, close parenthesis, you see that it is the exact same answer, 0.785398, yada, yada. Okay? All right, then we're going to come back here now to number 8. Number 8 is something that's needs a little special attention because this is from section 5.5. I'm going to ask a very basic question of this on the exam coming up on Monday, and it does have to do with substitution. It's called integration by substitution. And it comes from the fact that it is the reversal of using the chain rule, okay? And it is a matter of, tell you what, before I do the problem though, I want to go to the bottom, toward the bottom of the page and do another example and get the logic down of where this is coming from, okay? So let's look at this problem right here. Let's do, let me make one up here. So I've got x to the 4th, x to the 3rd minus 3. Let's just go x to the 4th minus 3, okay? And that is to the 5th power. Y equals that puppy right there. Okay, so, well, I'll tell you what. Yeah, that'll be good, that'll be good. All right, so here's the question. Now, when you take the derivative of this function, what happens? Notice you got to use the chain rule, all right? Notice you've got to use the chain rule. You got a function inside of a function. So when you do the antiderivative of it, you got to do the reverse of the chain rule. So there's a little sequence, a pattern to it that you can recognize. And let's see what the derivative of this turns out to be. Y prime, which would be dy dx, since it's in terms of x, would be you bring the 5 down front, reduce the power by 1 of the 5, and then you got to multiply by the derivative of the inside. That's the chain rule. So we end up with 4x to the 3rd. The final answer then would be, pull the 4x to the 3rd is to the 1st power, so is the 5. So I got 20x to the 3rd times x to the 4th minus 3 to the 4th power. All right? So notice what happens here. I've got this power is reduced by 1, and I got another exponent, I got another term out front that is 1 degree less than what's going on inside the parentheses, okay? That 3 is 1 less than the 4. That's an essential component toward using the reverse of the chain rule or using substitution. So the derivative is this. So if I do the antiderivative of this, watch this now. So if I have the antiderivative of 20x to the 3rd times x to the 4th minus 3 to the 4th, that looks like an incredible mess. You know what I'm saying? But notice this. You can see this power is to the 4th. This power is to the 3rd. That's evidence that a possibility exists that You got a chain rule that happens, you know, in the process of doing the problem. So as a result, what we can do is, this is where you use substitution. And so what you do is up here, in some book texts, you call it U substitution. I've heard that used, a phrase, by several different instructors. But if you make U equal the function that's inside the parentheses that you had to take the derivative of when you use the chain rule, then the derivative of that function is equal to 4x to the third. And you got to get used to using typing in a dx, writing in a dx when you take the derivative of a function in this type of situation, because it allows you, and I didn't put the dx here, that's kind of important when you got an integration moment. The dx is an important part of it. But you need to account for that when you're solving the problem and working it out. So it turns out that what we do when we substitute that in now back into the problem, it'll make it a simpler problem to work with. So what I'm going to do is I'm going to move that 20x to the third around a little bit. This is right next to the dx. I'm going to move it back there so it'll be a little more visible. So if I have the integral, I haven't changed it yet, I'm going to move the 20x to the third back there. Notice 20 has got the 4 in it. So that gives me a 5 times 4. So I'm going to leave the 5 here. X to the fourth minus 3. This isn't how you have to solve the problem. It's just trying to give you a good visual to see how the substitution is taking place. This is the same thing. That's the 20. But now we've got this 4x cubed here. That's our du. So now when we do the substitution, we can rewrite this now as the integral of 5. Plug in the u we had there, u to the fourth, and this becomes our du. Much easier problem to get the antiderivative, antiderivative of, to get the integrate. So what do we do? Now let's integrate. Now that gives us 5u to the fifth over the new exponent plus c, it's indefinite. So we end up with u to the fifth plus c. And now you resubstitute back in at the end. The problem started in terms of x, so you need to end in terms of x. If you end the problem and say the answer's got a u in it, it's wrong, okay? You used u for substitution. But the final answer turns out to be x to the fourth minus 3, which is u to the fifth plus c. So notice what it looks like. It is exactly what we started with, except there's a plus c on it now, which means that when we integrate, it could be any value out there, any constant could happen, okay? So let's do this last problem using this approach. So the idea is I'm going to go ahead and use substitution. I'm going to say u equals the number inside that I'm going to affect the chain rule. Notice I've got a cubed here and there's a squared there. Evidence that there's a good possibility of something going on here that's related to substitution. U equals that. Now du, the derivative, is equal to 3t squared, and the dt is important to account for that when we're doing the problem, cleaning it up, okay? So it turns out now that if I'm going to reorganize the order of the problems like I did before so you can just see we need something this time. It's not complete. I picked the problem before that gave us an answer and everything was there that we needed. But in this case, all we've got is t squared dt. We need a 3t squared dt. And this is the typical situation. It's rare that you're going to be able to just jump in and have everything there that you need. As long as it's just a constant multiple, you can introduce it, because just like multiplying the top and bottom by the same number, because you multiply by 1, if we multiply this function, if we multiply by 3 to get that 3t, I can also just multiply by 1/3. I need to do that, as a matter of fact. I multiplied by 3 and 1/3, so I did not change anything. So it turns out now we've got this situation. We've got 1/3. I'm going to rewrite this just so that it's visible. T to the third minus 3t squared dt. And again, you don't have to write it in this order. You can just, once you've got it in place, that the t squared could be in front and all this kind of stuff. But I just want to point out that this is our du. So we end up with 1/3 integral of, there's an exponent on that, isn't there? There's a 10 there. There's a 10 there. Pardon me for leaving that up. But anyway, that turns out to be u to the 10th du. Notice, here's our du. Here's our u. So now it's a simple thing to integrate, and that is the goal of using substitution. It simplifies the problem incredibly. So we end up with that. Now we're going to integrate. So the 1/3 is out front. We got to raise the power by 1 and divide by that new power, add c. And that's going to end up giving us u to the 11th over 33 plus c. Now we need to substitute back in our u. We end up with t to the 3rd minus 3 to the 11th over 33 plus c. Answer. Okay, an important part of doing the problem is now you checking to make sure it's right. You take the derivative of this, and you should get what you started with. Okay, so let's take a derivative of it and go. I'm going to go where I've got a little more room. Let's go y equals t to the 3rd minus 3 to the 11th over 33 plus c. Take the derivative of that. You got to use a chain rule. Bring the 11 down front. It gives me 11. T to the 3rd minus 3 to the 10th. The 33 is there. Got to use the chain rule when I'm doing the derivative. So I got to take the derivative of that, what's in the parentheses, which is times 3t squared. Now, and the derivative of c is 0, any constant. So now look what happens. The 11 and the 3 cancel with the 33, and what's left is t squared, t to the 3rd minus 3 to the 10th. Got it. And that's what we started with. So that's the problem. That's substitution. Practice the problems. There's a couple in the problems that I gave you from 5.5. Get into those, sapling 5.5, and take a shot. You got questions, jot them down, and get back with me and find out today during either class time or during office hours, right? And I ask you to upload that. Upload this file into, as you learn, there's an opportunity to do that. And I put that down at the bottom of week 15. There's an opportunity to upload your this file if you want to get credit for doing it, type thing. And that would be a good thing to do for me to see that you got it, okay? So, got questions, let me know. Be well, and keep smiling. Get ready for the test on Monday. Hit the sapling questions, and the exam on Monday will be coming soon, right? Be well.